Good morning. I'm KINSHUK, and today we're going to talk about OS level virtualization. Before we figure out what OS level virtualization is, we'll talk about the type of virtualization we know. So, what is virtualization? It's the ability to run many operating systems on the same hardware. Now, why do we need virtualization? Well, one, it provides flexibility for users, it reduces hardware costs, and it completely isolates these different users. There are four kinds of VM systems that we can use for virtualization. One is the traditional uniprocessor system, which is basically the hardware and one operating system running on it. The second one has a special VMM system, a virtual machine system, on which we can run many separate guest OSs. But here, there's no main operating system. You'll always have to run one of these virtual machines. Now, the third one is the one that we're all familiar with. We have our host operating system, the virtual machine running on top of it, and then many different guest OSs. The third one and the final one is where the VMM has actual kernel privileges. That means that the virtual machine itself can make kernel calls. The last one can be very useful to prevent traps, as we'll see about traps later, but it can be very risky considering that the virtual machine has straight up access to the kernel. So these are the platform types. It could be installed on on applications as applications on operating system, for example, VMware or VirtualBox, or it could be a bare metal architecture like we talked about earlier. No guest OS, just a virtual machine system. Now, this is the history of virtualization, how it started in the 60s, and now we have this super awesome technology called containerization. We'll talk about at the end. Now, this is the first virtual machine, one of the first. It was IBM 370, and it had no guest host OS. So it was specially made so that we can use many virtual machines on it. And this is the architecture. But one important problem it ran into was a trap emulate problem. So normally, for example, there's a command that requires kernel privilege that the operating system can run normally. Here, the problem was we had to trap that. So if there's a kernel command, the guest operating system will raise that kernel, then the VMM system will take that back to the kernel, the main kernel, the actual kernel, and that kernel will run it. Now, this is not that good on a normal x86 architecture. This is the architecture we all use. So phones are based on the ARM architecture, but computers are based on mostly on the x86 architecture. And it has a lot of performance problem, and not all privileged instruction produce trap. So it turns out to be a failure. So we went on to more modern technique like dynamic binary translation, where each of the binaries are intercepted and the instructions are changed so that it finally runs. It also has its own problems such that it's slow, plus there's so much storage. You're just basically creating a copy of the same binary again. So what does VMware do? We most probably use either VirtualBox or VMware, and they use some same sort of techniques. So these are the techniques used by VMware. So the input is a x86 hexadecimal, not the source code, but the hexadecimal code. It's a form of binary. So now the VMware will interleave the translation and will instead execute what needs to be executed to prevent traps. So you only translate when you need to execute. Why? It's like Java, where it's just in time. You only execute what you need to execute to save hardware costs, to increase performance, etc. And you make no assumptions about the guest code. It could be Linux, it could be Windows, it could be Mac, it could be any other operating system. And this is what we use because this is the best bet we have to run any operating system. So these are just how to convert the unsafe operations, not just the safe operations, but some operations might actually tinker with the kernel so much that it might cause a risk. So you have to create a shadow page table. So the page table are the set of registers with the page directory and the memory directory and everything. So you have to create a shadow page table so that it doesn't interfere with the actual page table. I would like to correct myself. It's not the register, it's the paging as in memory paging. So as you can see, this is the main table, and now we create a shadow page tables. So after this came the modern technique of para-virtualization, where instead of the normal OS, the guest OS was actually modified. So now you have your host operating system, on top of that the guest operating system, but the code of the guest operating system is modified to make it run faster, to increase performance, and to make sure all those privileged instructions run as fast as possible. So this is all about the virtualization and what types of virtualization you need. You need to create a separate CPU virtualization. You need to virtualize the memory, the IO, and you have to use these IA protection rings. So, but those also cause a very big problem. And this is why we turn to containers. Now we're going to get into the main gist of our topic, operating system level virtualization. As we saw back then, virtualization requires virtualizing everything. You have to virtualize the CPU, the memory, the input output, the display. But why do we need to? I already have a kernel. Can't I just use that? And this is how we talk about operating system level virtualization. So we talked about this earlier. There are these types of operating system virtualization. First is the native one, which is basically the same thing. It's what VMware VirtualBox does. You virtualize everything. Then we have the hardware assisted ones. Newer Intel processors actually come with VTX enabled, which makes it easier and faster to virtualize. If you go into setting on your virtual machine, you'll see there's an option for that. I'll show that in the end of this presentation. Then we have para-virtualization, which we talked about earlier. It basically modifies the guest operating system, and now the OS level virtualization. Here, so examples of these are FreeBSD, jails, Linux vServers, but most importantly, the name you have heard, Docker. So what's the difference? Normally, in top of the host OS, we have a hypervisor. A hypervisor converts all of those virtual OSs to one hardware so that it can be run. There's a high versatility because you don't need to define what OS you want to run, and it has very good performance. However, containers has one hardware and one kernel, and you use the same kernel. So in virtual machines, you create a separate kernel for everything. Here you use the same kernel, but you create many instances from the same kernel. So why is this better? One, you're not doing the same thing again and again. If I have a kernel, why do I need a new kernel? If I already have a Windows machine and I want to run Windows, I have the Windows kernel already, and I can use the same commands. So this is the ideal thing. This is why cloud computing took on. This is why Docker is so popular. It's the future. But what is the trade-off? This char is the perfect isolated system with 100% efficiency. There's no way to get this because this is an ideal system. In virtual machines, what we do is we have perfect isolation, almost perfect isolation, but the efficiency is low. So the more we try to isolate our guests from the host, the lower the efficiency gets. In the cloud systems, containerization or OS level virtualization, the isolation is not perfect. You share the same kernel, but that's not a problem unless you are doing something that requires changing the kernel itself, like we do in OS Lab. But in that case, you might be better off with a virtual machine. But for most majority of cases, virtual OS level virtualization is the best. Why? Because it gives you the most performance, It's the lightest, so you don't need to download everything, update. When the virtual machine stops working, how much toll it takes. You cannot do multiple things together, but those trade-offs go off when we use containers. So these are just the comparisons between hypervisors and containers. And this is the Zen 3 guest virtual machine, and has so many different processes it needs to run with the hypervisor, and that's what slows it down. So these are the implementations, and we don't need them. And most importantly, yeah, so now we come to actual experimentation. So as you can see, through the performance benchmarks, the performance of Linux and the performance of a vServer. A vServer is basically a container. So vServer and Linux, green and red bars are the same. There's literally no performance difference using a container, but you lose up to 30-40% of your performance while using a virtual machine. It's the same with the CPU and memory performance, and it scales. So when you use many virtual machines together, the differences add up. So if you're running 8 virtual machines together, your system will be very slow. While on the other hand, running 8 Docker containers or Docker instances or any container instances does not affect it that much, because they all share the same kernel. So this is one example, the Solaris Zones. It's present in the Solaris operating system. It's widely used in servers, but not so much in consumers. So these are the zones. Every zone contains a separate container. By default, there's only one global zone, so that it performs as a normal operating system. It's something it's part of Solaris. OS level containerization, it's built in to Solaris. So these are the same thing, daemons and file system and how it performs with containerization. Now, the other one is a OpenVZ. It only uses 1 to 2% of your Linux performance. So you basically get 100% of the performance. As you can see from the chart, the hypervisor has almost 300 times the performance difference. And this is on a server, a LAMP server. This is Apache server running, and these are the tests. As you can see, OpenVZ performs the best. Why? Because it uses containerization practices, but it's something that's built into the Solaris operating system. And this is just how it works. Now that we have studied the theory behind containerization and OS level virtualization, let's try something a bit more hands-on. Here we'll play with Docker. It's the most widely used container, and here we'll start a new playground. So in a playground, you have a virtual sandbox, which basically means instead of running this all on your computer and risk harming it, you can use a server. So creating a new instance is basically a new server. So here, let me show you, it's running Linux. And now we'll start off by using this basic command, docker run -dp 8080 docker getting started. One good thing about Docker is you don't need to have the Docker images or normally you'd say your virtual machine on your system. Docker can pull these from the internet. So if you already know you need a Linux system, you don't need to download it. Docker can automatically download it for you. So it's running and it'll show up at port 80 shortly. As soon as it does, we'll see a point here that says 80. As you can see, as soon as I open port 80, I get this page, and you can see that it's running directly on the computer. It's not a website. So it's running from the Docker container. So this just explains what we did. we ran a Docker command with -p for detached mode. Detached means that the output wouldn't be visible on the terminal. -p is just mapping the ports, so port 80 of the guest is port 80 of the host. And now we can start creating an application. So suppose you have an application you need to run on a server. How do you do that? Well, you can use Docker. So instead of building an application, we'll use an already existing application, this app called app.zip. Let me upload it right to my container. To upload to this virtual machine, all I need to do is drag and drop. And as you can see, it'll say uploading file. Now that the file is uploaded, we can run ls. And here's the file. We can unzip the file, unzip app. And if we run ls again, we see the directory is there, app. Let me go to the directory, cd app, and now we can see all the files. So src contains our app. It's a standard Node.js app. You don't need to know what Node.js is. It's just a web server. It's just a web app you need to run. So now in the same directory, we'll have to create a Docker file. What a Docker file does is it tells Docker what kind of image to build. Now for this specific program, this is what we need to build. So we'll have Python, G++, make, APK, and add. And it will be created in the app directory from this node right here. And it'll automatically run this command when it's done. It'll automatically run this with these arguments, node, source, JSC. So let me copy that. And I've created a new file with touch. And as you can see, it'll be there. Yeah. So now we can use echo, paste all of that, and send it to the file, the Docker file. And if you cat Docker file, you can see that that text is indeed there. Now we can finally go to the main step, which is creating a Docker image. Now here we have to create a Docker build command. Oops. Yeah. Now let me do the Docker build command. Now it's building everything, as you can see. It's pulling the data from node 12 that we defined right here. It's running these commands. It's installing all these things we asked it to install. Right here, we asked it to install APK, add, no cache, Python, G++, and make. And it's doing all that. Now, it's resolving the packages. So all of this is done by Docker itself. You don't need to do any of this, which is one of the major reasons we use Docker. When somebody says this software runs in my computer, even in our lab, someone says this runs in my computer, but it doesn't run in your computer. So what's the problem? Well, Docker can fix this issue. You can directly download their images. So your computer will be exactly the same as their computer. And it's almost done. Now that when we have this app, I'll run it on port 80. When it's completely done, I'll run it on port 80. Yeah, it's completely done now. Now I can run this app. It's lagging a little. Yeah. Now I can run this app on port 3000. And this will create the app we just made, the Node.js app. We downloaded, yeah. So now I can open port 3000, 1, 2, 3. And in the next page, our Node.js app is running. See, this is the app we downloaded. It's like magic. So we're running a website or a web application on a server without even leaving our server. We just create a new container. We just created a new container, made a Docker file, and we just pushed all our files onto it. How easy it is it? We just create a new Docker file in the directory of the software or the application. Then we add all the information needed, the files you need to install, the command you need to run, and we just say Docker. That's it, Docker build. And now we have the Docker image. And it's simple as that. And this is one of the main reasons why containerization, see, this is the web app right here. Nothing, you don't need to build your own computer proper, you don't need a proper LAMP architecture. And this is one of the main reasons why containerization is so important. It's the future of virtualization. The idea has existed for a very long time, but this is the main reason, this is the main time when it's coming into play. Next, I'll show how we can use WSL, that is Windows Subsystem for Linux, and we can basically run Ubuntu in my Windows system without using anything. No virtualization, no Docker, and no virtual machine. I can run Ubuntu directly on a Windows terminal. I'll see. Now that we are familiar with Docker, we'll get into WSL, Windows Subsystem for Linux. But before that, an important question. Which desktop OS do you use? Linux, Windows, Mac? You probably use one of these three. But what if you need to use something else? Well, that's what Windows Subsystem for Linux is. So I have a Windows machine, and I'm guessing most of my friends do too. But Linux is a very essential part of being a developer. You cannot learn development without using Linux. So we'll use Windows Subsystem for Linux. And what it does, it allows us to use a full-on Linux operating system inside of Windows. And it's not like a container or a virtual machine. It's just running side by side. So WSL1 only allowed Windows to run native binaries. So it's not a full-blown operating system. It just allowed you to run the binary. But with WSL2, you get the whole Linux kernel inside Windows. So I'll get you the steps on how to enable it. Press Windows key, type Windows features, and click on that. Then this window will pop up. Here you have to click Virtual Machine Platform and Windows Subsystem for Linux. Click OK and restart your computer. This is one way. The other way is using a command line. Click Open Windows PowerShell. Windows key, PowerShell, enter. Then enter these commands. 1. Enable Windows optional feature online, and the feature name is Microsoft Windows Subsystem for Linux. Second, enable Windows optional feature online, and the feature name is Virtual Machine Platform. Need the Virtual Machine Platform because this is what it's used to run the operating system. Now you just restart your computer, and this is a very important step. You need to set your default version to 2. WSL1 does not support an operating system. Now, downloading an operating system is as easy as installing an app on your phone. For example, I'll go to Windows Store right here, and all I need to do to download an operating system is I'll just search for Ubuntu, click on it, download. That's it. Now you have a whole Ubuntu inside your Windows computer. And it's not running via a virtual machine or a Docker container. See right here, this is Ubuntu running inside Windows. Look how snappy and quick it is. See, Linux. Now, this is normally virtual machines give you a proper isolated sandbox environment. But that is not what we need. I as a developer need to run my application on both Windows and Linux. What I can do right here is open a Windows terminal. Let me start it again. I can just start a Windows terminal right here. So this is Windows, of course, Windows PowerShell. And all I need to do is click this, and now I have Ubuntu running side by side. And the best part, they're sharing the same space, they're sharing the same directory. So c/users/kinshuk, and right here mount /c/users/kinshuk. I can do directory lists all the files in a directory on Windows. So these are all the files. And I can use ls. Again, these are the same files. So I can run Ubuntu side by side with Windows. The possibilities are endless. This can go from doing sudo apt-get install. I'm just, of course, not going to download anything, to running bash, git, anything. So you get the power of running both of these. You can run Ubuntu, Windows together without any performance hindrance. This has been Windows Subsystem for Linux, and I hope now that you have seen the end of the video, you appreciate containerization and operating system level virtualization and more, and you've learned how this is so helpful in the future. Thank you.